Hello, today we're going to talk about tangent planes and how to use them to do linear approximations of surfaces. So since we're working with multivariate functions, when we when we try to think of this idea of finding a line that's tangent to a surface, it doesn't really make much sense because the problem is that there are infinitely many lines tangent to a surface at any given point. Okay, and I have an image down here below that shows a surface underneath. It's kind of a bluish surface underneath, and there's this green tangent plane to that surface. And on the picture, we see two tangent lines at this point P. But honestly, I could draw so many more as I'm demonstrating right now. All of these lines that I've drawn are tangent to the surface at that particular point P. So that's just to demonstrate how unrealistic it is to think that we could come up with the tangent line to a surface at any given point. Our functions are solids. They have greater dimension. And so when we want to talk about something that's tangent to our surface, maybe it's better for us to think of getting the thing that would capture those infinitely numerous tangent lines to our surface. And the only thing that could do that is a plane. Okay, so if we're focusing on our surface, and if our surface is differentiable everywhere, and we zoom in on the function at a point, the surface itself starts to look like a plane. I have this image from our textbook that gives you that same sort of idea. So here in figure 2, we're looking at an elliptic paraboloid in the first image, z equals 2x squared plus y squared. Notice the window on it. The x values are going from minus 4 to 4, y is minus 4 to 4, and z is going from minus 20 up to 40. And what we see is the elliptic paraboloid itself, but then also a tangent plane underneath it. And that tangent plane is at the point 113. So what they did in the next image, the second image, is they zoomed in. So now the x and y values are going from minus 2 to 2. So we're seeing a smaller part of the surface in the tangent plane. And notice how we see less curviness showing up in that elliptic paraboloid. If we go to the third image, that's where they've done the most zooming in. Now what we have here is that x and y are going from 0 to 2. And remember, we're focused on the point 113. So when we have this window from 0 to 2 for x and y, 1 is right in the middle. And so we're talking about a point that's like right here, whoops, in the middle, hold on, right there in the middle of the surface. But notice that the surface itself is almost flat. Like we've zoomed in so far that the surface itself is starting to look like a plane. And that's the idea, is that if we were to zoom in at a point on a surface, it would start to look flat, okay? The surface starts to look like a plane. And that plane, if we were to actually get the equation of the plane right there, then it's called the tangent plane to the surface. And then what it will have is all the possible tangent lines to the surface at that point, okay? So if we're trying to come up with this tangent plane, a good question to ask is, well, which tangent lines are the most important ones, right? We need some information from our surface, and so maybe the tangent lines, maybe some of them are special. And it turns out that a couple of them are. In particular, the tangent lines that point in the x direction and the other that points in the y direction are super duper important, okay? So in this particular image, what they've done is they've taken a cross section of the surface. This is a C1 cross section. And then what they did is they found a tangent line to that cross section, okay? And so that tangent line, it's hard to see in 3D, but that tangent line is running along a fixed y value. So this is the tangent line that corresponds with the vector del z del x, right? So remember that our partial derivative with respect to x will point in the x direction, and that gives us how things are changing in the x direction. Similarly, They did the same for C2, right? C2 is a cross-section of the surface, and it is running parallel to the y-axis. So we're on a fixed x value, and then T2 is a tangent vector, or a tangent line, sorry, to the surface, and it runs parallel to del z, del y, okay? So those are the most special vectors that we can come up with that are tangent to the surface at the point. Now, if we take those tangent vectors, or not tangent vectors, sorry, those tangent lines, and we focus on the del z, del x, and the del z, del y, and we evaluate those at the particular point, what we're going to come up with is the slope in that direction. And that's what we want. So right here, what I have is the point slope form of a plane. And I'm calling it that for a very particular reason, because it's in the point slope form of a line format, which is something that we know and love, hopefully, from college algebra. So in the point slope form of a line, you would have a point. So we have x naught, y naught, and z naught. That's our point. The slope is coming from the f sub x evaluated, remember it has to be evaluated, at the point x naught, y naught, and then f sub y is also part of our slope, right? So since we're in 3D, we have to have two slope functions giving us slope values. Okay, so the blue is giving us the slope values in the x and y directions. And then the point P is x naught, y naught, z naught. So P is a point. Okay? And then, of course, we would normally solve for z. So we would move the z naught over to the other side of the equation. And then this would be our formal equation of a tangent plane. Okay, so if we're asked to come up with the equation of a tangent plane, it looks like there are a few ingredients that we need. We need a point, all right? So if we don't have a point, then we can't go anywhere. So they need to give us a point. They may only give us the x and y value, and that's okay. If we have the x and y value, we can plug them into the surface to get the z value that goes with it. The next thing we need the partial derivatives with respect to x and y from our surface, and then we need to evaluate those at the given point. And then we're just going to plug it all in, and we will have the equation of a tangent plane. Now, one thing I want to make very, very clear, and I want to go back to that picture that I had before, is that the tangent plane can be used to approximate a surface. So notice the third picture again. In the third picture, we're zoomed in enough so that the surface is starting to look flat, and the tangent plane is starting to look like a really good approximator of the surface. They're almost identical, but not quite, ever so slightly off from each other. And so this next section about linear approximations, I want you to understand that we're not calculating anything different from the equation of a tangent plane. So don't think that you need to memorize two things when they are really the same thing, okay? What we're saying with a linear approximation, though, is that once we have a plane that is tangent to a surface at a point, we could use the plane to make an approximation of the surface at a different point, okay? Not at the same point, but at a different point. We're going to say, I wonder if this surface can tell me the function, or this plane can tell me the function value just a tiny bit away from the original point. So this linearization function is what we call the linear approximation. So what we say is that z, our original surface, is approximately this linearization function. And let's just notice some of the differences and the similarities. So notice the f sub x of AB. And up in the equation of a tangent plane, notice the f sub x of x naught, y naught. It looks like in the linearization function, a and b represent x naught and y naught. That's the difference. That's it. That's just about naming convention. That's it. X minus a, and then in the equation of a tangent plane, it's x minus x naught. So here it's very clear. A is x naught. F sub y of AB, f sub y of x naught, y naught, those are the same thing. A is x naught, b is y naught. And again, we have y minus b, y minus y naught. So b is y naught. And here's the last one that is sometimes a little tricky for people to wrap their heads around. F of AB is the same as z naught, okay? Because z naught is equal to the function evaluated at x naught, y naught, right? And so if we have if we know x naught and y naught, we also know a and b because they're the same. They're interchangeable. It's just a matter of your book using slightly different notation for two different things that are actually the same. So don't let the naming convention trip you up. They really are the same, okay? All right, so the thing to stress here then is that our function is approximately the linearization function in a really small neighborhood near the point at which we found the linearization function, okay? And so this approximate symbol is very important. You would never say that your function is equal to the linearization function. They are not the same thing, okay? Your function is approximately the linearization function. All right, so let's see how we can find a plane tangent to a surface. In this particular example, S is a surface, Z equals Y times sine of X. So we could define S to be f of xy, which is equal to y times sine of x. Remember, Z and f of xy are interchangeable. We're going to find the plane tangent to our surface S at the point pi sixths, 2, and 1. So what we have there is that x naught, which is equal to a, is equal to pi over 6. Y naught, which was equal to b, is equal to 2. And z naught, which was equal to f of x naught, y naught, is equal to 1. And we could check that z naught actually makes sense. We just go back to our function and plug in pi sixths for x and 2 for y. So if I plug in pi 6 for x, I have sine of pi over 6, which is going to be 1/2. And then y is 2, so 2 times 1/2 is 1. It makes sense. Z naught is 1, okay? All right, so those are all the ingredients that we have. We want to find a tangent plane. Remember that when you're being asked questions, it's always important to ask yourself, what am I being asked for? And if I know what I'm being asked for, then I should write down that thing. So if we're being asked for a tangent plane, then I want to write down z equals f sub x of AB times x minus a plus f sub y of AB times y minus b plus f of AB. Okay? So now that I have the equation sitting in front of me, it's a lot easier for my mind to accept that I need to find my first partial derivatives, first things first. Okay? So let's do that. Remember, f of xy is z, so when I'm finding f sub x, I'm taking del x of y sine of x. Y is just a constant here, so I focus on my sine of x. The derivative of that with respect to x is cosine of x. Okay? F sub x of AB, well, AB is pi over 6 and 2. So I'm going to plug those into my first derivative there. I get 2 cosine of pi over 6, which is 2 times root 3 over 2, which is square root of 3. All right, so I have one of my pieces. Another piece I need is f sub y, which means I will take del y of my surface, which is the y sine of x. Now x is a constant and y is my variable that I'm interested in. So the derivative with respect to y of y sine of x, well, just focus on the y and the derivative is 1 there, and sine of x is just a multiplier. All right, now I will evaluate f sub y at pi over 6 and 2. So that means I get sine of pi over 6, which is 1/2. Okay, so I have 2 of my pieces that I need. I'm just going to highlight those. It looks like actually I can just go ahead and plug everything in. All right, so the next thing to do is substitute into the equation. So z is equal to f sub x at the point, which is square root 3, times x minus a, where a is pi over 6, plus f sub y at the point is 1/2, times y minus b, where b is 2, plus our z naught, or our f of a b, or f of x naught y naught, they're all the same, and it's 1, so we're going to be adding in 1. And this right here is the equation of the tangent plane. We could leave it like this, or of course we could also distribute to simplify things. So we could say z is equal to square root 3x minus pi square root of 3 over 6 plus 1/2 y minus 1 plus 1. Those are going to go away. And so this actually is a simplified version to have expanded it out a little bit. And so this is the equation of the tangent plane. Not too bad, as long as our surface isn't too complicated. We really only had to take 2 first partial derivatives and evaluate them, and then literally just plop everything into the equation. All right. Now, I want you to notice something. Notice if I was to move everything to one side of the equation and move the constant to the other side, I'm going to write that out. I would have square root 3x plus 1/2 y minus z is equal to pi square root 3 over 6. So this is standard form. So it is the standard form of a plane. The coefficients of the plane in standard form give us the components of a normal vector to the plane. In this case, n, the normal vector to this plane, is equal to the vector with components square root 3, 1/2, and -1. So it's just an observation right now. Not something that will be asked in homework or anything, but really to tie it together with what we learned in 12.5. Okay? Even a tangent plane will have a normal vector to it. All right, next problem is kind of different, and I chose it because it is so different, and it requires us to do things different from the previous problem. So in number 2, S is a cylinder, x squared plus y squared equals 4. We're going to find the plane tangent to S at the point 1, root 3, and 5. So the cylinder x squared plus y squared equals 4 looks like this. I'm not the best drawer, but I can get something that resembles what we're working with on paper. Okay, so this is our cylinder. It is running parallel to the z-axis, and it has a radius of 2. It is centered along the origin. And our point P, 1, root 3, and 5, is in the first octant, somewhere along here. Let's see, we're up high on Z, so I'm going to place it right here and just know that this is in the first octant, okay? So we're trying to find a plane that is tangent to the cylinder at that point. Any plane tangent to that point is going to be parallel to the cylinder. So this is the point on the cylinder in the first octant. So we can say that the surface, just to put out everything I verbalized into words on paper, the surface is parallel to the z-axis. This means the tangent plane to this surface will also be parallel to the z-axis. Therefore, z will not be a part of the equation. Only x and y will be involved. So what we're using here is information that we learned in 12.6, that a surface equation that is missing one of the variables will always run parallel to that variable's axis. And so we're kind of going in reverse. We're saying our plane will be parallel to the axis that is the z-axis. Therefore, z will not show up in the equation of the plane. Okay, so it's just kind of reading that theory backwards a bit. So what that means is our tangent plane is going to look a little bit different. And what it's going to look like is y minus y naught equals m times x minus x naught. And that should look super duper familiar. That looks like the point slope form of a line in 2D, right? So let's just write this out here. This is the point slope form of a line in 2D. In 3D, this is the point slope form of a plane parallel to the z-axis. Okay, this m right here, this is going to be del f del x, or f sub x, at the point A, B. And I guess really it's at the point A in our case, because, well, we'll see. Let's walk through this a little bit. Okay, so because the point and let's see, what was our point again? 1, root 3, and 5 is in octant 1, where y is greater than or equal to 0, we can solve for y in our surface. So what that means is we're looking at x squared plus y squared is equal to 4. That's our surface. We're going to solve for y. So y squared is 4 minus x squared. Continuing on, y is normally equal to plus or minus the square root of 4 minus x squared. But because there's this declaration that y is greater than 0, that's why I'm going to go in and say, nope, we only want the positive square root of 4 minus x squared, okay? Now we can define, we can go ahead and, let y equal f of x equal the square root of 4 minus x squared. And then we need del f del x, or f sub x. So I'll use the f sub x notation. And what that's going to mean is we're going to take del x, which it turns out it's really not a partial because we have an explicit function of one variable here. So I'm going to stress that ultimately we had a two variable function there. But if we take del x of 4 minus x squared to the 1/2 power, we're going to get 1/2 times 4 minus x squared to the negative 1/2 times the negative 2x when we use the chain rule. All right, so del f del x is, when we simplify, we get negative x over the square root of 4 minus x squared. And now we need to go ahead and get that evaluated at our point. Remember, our point is right here. We've got 1, square root 3, and 5. And it looks like we're only concerned about the value 1. So let's go ahead and get that. F sub x of 1 is going to be negative 1 over the square root of 4 minus 1, which gives me negative 1 over the square root of 3. And it's fine to leave that not rationalized. Leave it as is. All right, so this is our slope, our m. So we're going to plug this into the formula up above for a tangent plane, and we're going to get that our plane, our tangent plane, is going to be y minus y naught is the y value in our point, which is root 3, equals m, our slope, which is from our first partial evaluated at x naught. So we get negative 1 over the square root of 3 times x minus x naught, which is 1. And then that's it. We can simplify this, of course. We'll distribute and solve for y. Y is equal to a negative 1 over square root 3x plus 1 over square root 3 plus the square root of 3. And that simplifies to be y equals negative 1 over square root 3x plus 4 over the square root of 3. Okay, so that's the equation of our tangent plane. And this does not have a z in it, so it'll definitely run parallel to the z-axis. And if we were to graph it in addition to the cylinder using some sort of 3D software, then we would be able to see this plane right alongside that cylinder, right on that point, 1, root 3, and 5. Okay, so let's see, we could have used either one of these equations, these tangent planes that we found, in order to approximate the surface at a different point, but we'll do that in our next example.